This is the Unit 3, Part 3, second video in the series. If you just finished watching the first video, you will know that the whole point of this video series is for you to be able to determine the three-dimensional geometry of just about any molecule using VSEPR theory. This particular video, we're going to spend a lot of time talking about molecules that have 4 or fewer electron domains around the central atom. So we might as well just get started. So let's pull this down. So if we look, we have 2 molecules. We have carbon tetrafluoride here, and we have methane here. Now, if we're going to really look at this, let's realize that we need to count electron domains and bonding domains in order to determine the molecular geometry. So we're going to count that each of these, and I have 2 different examples, but both examples have 4 electron domains, 1, 2, 3, 4, 1, 2, 3, 4, around the central atom, and there is also 4 bonding domains around the central atom. So realize VSEPR theory says that those electron pairs are going to want to be as far away from each other as possible. So if those electron pairs want to be as far away from each other as possible, what we need to realize is that they're going to take a shape that looks like this. And I'm going to make this a little bit bigger so that maybe you can see it. We are representing the molecule here in 2 dimensions. So when we do that, we push the bonds as far away from each other as we can as a bond. And when we do that, you can see that they are 90 degrees apart, but that's because they're written on a 2-dimensional surface. Here is a 3-dimensional representation of what it looks like. And when we do that, and we do the calculations, when we space 4 things, 4 bonds, as far away from each other as possible, you'll note that this bond angle between this bond here and this bond here will be at 109.5 degrees. And that's true for the most part anytime something has 4 electron domains around the central atom, because you're pushing all 4 electron domains as far away from each other as possible. So whether there's a bond in it or whether there's a free electron pair in there, the bond angle should be somewhere right around 109.5. So what we do is we're going to give this thing a particular name. The name of this is called a tetrahedron. It's either called tetrahedral or tetrahedron, okay, which would be spelled tetrahedron, O-N. So let me take this guy and we'll make it a little smaller here, and then what we can do is we can say, hey, look, this guy, we'll put it right up here because that's what methane looks like. And of course I can get rid of this here. But we should probably write down that the angle of tetrahedral compounds is a 109.5. So then you say, well, Mr. Walsh, what about things that have 4 electron domains but have less bonding domains? So let's take a kind of a straightforward example like ammonia. Ammonia, if we look at it, and I'll do this in a different color, ammonia has 4 electron domains, 1, 2, 3, 4, but when we look at it, it actually has 3 bonding domains, 1, 2, 3. Now, when we look at that shape is based on, and this is the shape of ammonia right here, that shape is based on only where there are bonding domains. Yes, there are electrons, free electrons up here, but those electrons do not contribute to the overall shape or the geometry of the molecule. What they do is they contribute to the bond angle, so that there are 4 electron domains controlling the bond angle, but there are only 3 that control the shape. So if we take a look at this guy and compare it to the tetrahedron here, so I'll bring this back down and we'll make this, and we'll really compare it. This guy here looks almost like this guy, just without this top thing there. And so that gives it the shape, the name of its shape, or its geometry. And that is going to be pyramidal. Now let's keep in mind that the bond angle is controlled only by the number of electron domains. So the fact that this guy has 4 electron domains means that the bond angle between this guy and this guy is still going to be somewhere around 109.5. In this case, it's actually going to be 107 degrees. But the idea is that the bond angle is controlled by the number of electron domains. So we can take this and we can shrink that. And so the shape of the molecule is controlled by the bonding domains and the electron domains. I'll put this down here so that you can see everything. So let's speed up a little bit now. Now that you get the idea, we can take the next example, and that's water. So we'll do water in a different color, so that water has 4 electron domains and 2 bonding domains. And now when you have this, again, it's kind of based off the tetrahedron. It kind of looks like a tetrahedron, but it only looks like a tetrahedron that has 2 sticks pointing off of it, maybe this one and this one. And so when you look at that, the bond angle again is going to be right around 109.5. In this case, because it's a little because there's 2 pairs of electrons, it's a touch smaller, so it's 104.5 degrees. But again, it's still right around 109.5. And the most important thing is that it is not 90 degrees as we would have represented on a 2-dimensional surface. The bond angle is 104.5. And if I take this, you can actually see how they kind of overlay. I can take this and manipulate. I can turn it. Look. And then this kind of looks almost exactly like that. And then this shape then, let me put that there. This shape is actually what we call bent, or sometimes we call it V-shaped. Now the last one in this series, as you can guess, is going to be something like this guy, where you have 4 and 1, 4 electron domains and 1 bonding domains, and this thing is linear, it's a line. And the only funny thing is because there's only 1 part to the angle, there's not a second line to form an angle anywhere. We actually never say that this has a bond angle, so we're just going to say Na. That doesn't mean that all linear molecules have a bond angle, but anything that has only 1 bonding domain will always just be a linear molecule with no bond angle. Now if we speed up, here we go. We're going to move up to or move down, I guess, to 3 electron domains. So here we have boron trifluoride, has 3 electron domains, and all of those electron domains, have bonds in them. They're all bonding domains. And so if we're going to try to evenly space those around the molecule, around the central atom, we get something that looks like this, and I'll make it bigger. But you can see that there are 3 atoms evenly spaced around the central atom. So the name of this guy is going to be Trigonal Planar. It's called trigonal because if we look at it, it looks kind of like a triangle. It's called planar because it's flat. What is the bond angle? The bond angle is actually kind of easy to remember because it's 120 degrees. If we take a circle and split it in 3 equal parts, that's 120 degrees. Now what if we go down to the next one? Well, you can see a pattern emerging here. So we have, instead of 3 and 3, now we're going to do 3 and 2. So this is 3 electron domains, 2 of which are bonding. And this looks almost exactly like the previous one here. It looks almost like this, right? Looks like that, except now we only have 3 electron domains and 2 bonding domains. So now what's the difference? Well, this looks like this. And again, keep in mind that you do have two electrons that are repelling here so that this shape will look like a bent molecule. So what makes this bent different from this bent here? Well, it's the bond angle. The bond angle for this molecule is 120 degrees as opposed to 104.5 or 107 or 109.5. So we're going to keep the bond angle the same. And the last one in this series would be something like oxygen, where you have 3 and 1. And again, that's linear. That's pretty straightforward. Now, let's go down again. So now we have something like carbon dioxide. Carbon dioxide has 2 electron domains and 2 bonding domains. Carbon, the central atom, has 2 electron domains, 2 bonding domains. And now the shape here, when we take and we put 2 things around a 3-dimensional object and put them as far away from each other as possible, we are going to have something that looks like this. This, then, let me make sure that I'll spin this and make this look very similar to that. But we look at that. That thing is a line. It's a linear molecule. So the shape here is going to be linear. Now this does have a bond angle because there are 2 sides to the angle, so the angle there is 180 degrees. Last is going to be this guy, where you have 2 electron domains and 1 bonding domain. And again, this is linear with no bond angle because there is no angle there. And then the last molecule that we have is going to be this guy, where there's only 1 electron domain and 1 bonding domain, and of course that is going to be linear. Okay, so now try it yourself. Pause the video and see if you can determine these shapes. So I assume that you pause the video. When you pause the video, here we're going to have, so 4 and 3, the shape is pyramidal. And the bond angle of this is 107. Now, here we have urea. This is a compound found in your pee, of course, urea. And here, around the central atom, we have 1, 2, 3 electron domains, and we have 3 bonding domains. So which one is 3 and 3? This is trigonal planar. And trigonal planar has a bond angle of 120 degrees. And you may now see something like nitrogen triiodide. You are going to have to know the formulas and be able to write a Lewis structure. And I picked this one up for a reason. When we do this and we do the Lewis structure correctly, and my Lewis structure is sloppy, I apologize, but when we finally get all the stuff around it, you'll know that this has 4 and 3, 4 electron domains, 1, 2, 3, 4, and 3 bonding domains. So the molecule is actually pyramidal with a bond angle of 107.